Hey guys, I hope it's going well. I hope you are comfortable and settled in, ready for the next hour of this video. Just kidding, it's not an hour, but I made you look. So it's only a couple minutes, so let's go ahead and jump in. This first part should be a review, a little bit of what you remember about ratios and proportions. So hopefully you remember that a ratio is a comparison of two quantities using division. The ratio of quantities A and B can be expressed as A to B, A colon B, which we would still say A to B, or A over B, where B does not equal 0. So some examples, you can see down here we have 31 over 18 is one example. Another example is 3 to 2. And the last example is 16 over 9. So those are the three different ways that we could write a ratio. Now it is important to note that we do simplify ratios whenever we can. So for example, if this first one had said 32 to 18 instead of 31, we would have reduced that to 16 to 9 by dividing both of those by 2. So it is good to notice that we try to reduce those ratios whenever we can. Alright, so that's our review of ratios. Let's jump over to proportion. So proportion is just a comparison of two ratios. Alright, so proportion is a comparison of two ratios. So for example, we could have a proportion that looks like this. A over B equals C over D. That's comparing the ratio A to B and the ratio of C to D. Now in order for this proportion to be true, these two ratios must be equal. The way we look at that is we call our parts of our proportion different things. So these two pieces, we call these our means. Those are our two mean values. And we call these two our extremes. Okay, so B and C, those two places, we call those the mean, and then A and D would be our extremes. So let's see how we're going to test that. Product property tells us that in a proportion, the product of the extremes equals the product of the means. So for example, if we have that same one that we just had, A over B equals C over D, the product of the extremes equals the product of the means. So let's take the product of our extremes, A times D, and we say that that equals the product of our means, B times C. So again, if this ends up being a true statement, then that proportion is in fact true. So let's check one out where we do it in numbers. Let's say that we're comparing the two ratios. Let's say we have the ratio 2 over 5, and that equals the ratio of 6 over 15. Let's test that. Let's take these two values, so 2 times 15, and set that equal to 5 times 6. Well, 2 times 15 is 30, and 5 times 6 is also 30. So since that statement is true, this proportion is true. Okay? Well, here's a difference. Say that it tells us that the proportion is in fact true. And we need to figure out what value of x makes that proportion true. So let's use that same side that we had, 2 over 5. And let's say that equals x plus 1 over 10. We would do this the same way we did before. We would take these two and we'd say 2 times 10 equals, we would take these two, so that equals 5 times x plus 1. So see if you can figure out what x equals. Alright, let's pick back up, see if you got it right. So 2 times 10 is 20. You have to distribute this 5, so we get 5x plus 5. Now I can subtract 5 from both sides. Alright, now I'm kind of out of room, so I'm going to erase my problem up here and kind of finish up my problem up there. Hopefully you didn't run out of room on your paper and you were able to keep working. So when I subtract 5, I got 15 equals 5x. So if I divide by 5 on both sides, x equals 3. So for that value of x, that makes the proportion true. Right? So that'll help you out with some examples of proportions. Now let's see how we're going to use these ratios and proportions as we keep going and talking about triangles and figures and polygons. So similar figures, that's where we're going to use these ratios. Similar figures have the same shape, but not necessarily the same size. So for example, this rectangle and this rectangle are similar. They have the same shape. They're both rectangles, but not necessarily the same size. Obviously, one of them is bigger. So those would be similar figures. Now, a non-example would be, so here we have this rectangle, and it would not be similar to this circle. They're not even the same shape. So those two would not be similar figures. So with similar figures, we're talking about things that have the same shape, but they're not exactly the same size. They're not congruent. They're just similar. Okay? So let's look at this. So to be more specific, similar polygons, two polygons are similar polygons if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. So you can see in the diagram we have an example of similar polygons. All right? Now remember, when we said that things were congruent, we used this symbol, an equal sign with a little squiggle on top. Well, now when we talk about things being similar, we just use that squiggle. So that symbolizes similar. All right, so in our picture, we can see that shape ABCD is similar to shape EFGH. We know that because their angles are congruent. You can see that angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, and angle D is congruent to angle H. And you can see, just like as we did in the congruency statements, those are in the same places on their similarity statement. Now, it's not enough to say that the angles are congruent. You also have to see that the sides are proportional. So you need to see if the length of side AB over the length of side EF equals the ratio of all the other sides. And at the end, if you get that all those ratios were equal to one value, then you have two similar polygons because their sides are proportional. All right, let's look at an example. So let's identify the pairs of congruent angles and the corresponding sides. All right, well, thankfully, they've already done some of the work for us. We see that angle Z is congruent to angle R, which is already drawn. You can see with our congruency marks. We see that angle Y is congruent to angle Q. Again, that's already marked for us. And by the third angles theorem, angle X is congruent to angle S. So we can mark that. So we do know that all the angles are congruent. That's good. But we still have to test the sides to see if they are actually proportional or not before we can say that these two are similar shapes. All right, so let's look at the things that it said are similar. Let's see, we have angle Q or side QS right here. And that side would be similar to side XY. You can tell by seeing where the angles are. So side XY over side, we'll say SQ to go in the same order. All right, let's set up the rest of them. So all right, so XY over SQ. So let's see. The next side, we would have XZ over SR. Let's write that XZ over SR. I'm going to have to start writing smaller. And my last one is side ZY and side RQ. So let's see if I can fit that in there. All right, barely fit. Okay, now that I have that all written out, let's go ahead and start putting in our numbers. All right, let me erase all of this so we can kind of see a little bit clearer. There we go. All right, get some of that cleaned up a little bit. Okay, now let's start putting in numbers. So side XY is 6, side SQ is 9, side XZ is 9, and side SR is 13.5, and side ZY is 12, and side RQ is 18. So based on the information, can we say, in fact, that this is a true proportion and that these figures are similar? What do you think? Okay, well, we could reduce these fractions. We know that 3 goes into 9 and to 6. So we get 2 over 3. Now you may not know for sure about 9 and 13.5, so let's take a break on that one for just a second. We can come back. But we know that 6 goes into 12 and 18, so that reduces to 2 over 3. So let's see if we can reduce 9 over 13.5 to 2 over 3. So even if you needed to use a calculator to figure that out, you could see that that would equal, in fact, 2 over 3. So since all three of those were the same, then this is a true proportion and these figures are similar. So there we go. So we could say that triangle QSR is similar to, and then what would be the similarity statement that we would put here? See if you can complete it. Is that what you got? That would be the similarity statement for these two triangles. All right, let's look at one. So the last thing we're going to look at is something called the similarity ratio, which is the ratio of the lengths of the corresponding sides of two similar polygons. So in just a little bit, as we get into our lesson tomorrow, we're going to be calling this a scale factor. That's what we're going to be doing on the graph. So our similarity ratio tells us pretty much what we're doing to one triangle or shape to get to the other one. Did you make it bigger, smaller, and by how much? So for example, let's look at these two triangles. The similarity ratio of triangle ABC to triangle DEF is 3 over 6, or 1/2. All right, you can see this because as we write the proportions of our sides, you can see so side AB over side DE is 3 over 6. And since all of the angles are congruent and the sides are proportional, we can say that these two are similar triangles. And the similarity ratio is 1 over 2. That's the ratio of those two sides. Why don't you see if you can figure out what the ratio of the sides of triangle DEF to triangle ABC would be. Once you finish that, you'll be done for today. We're going to have some homework on this tomorrow, and then we'll be moving on with the rest of the section. So this will give you time to absorb this and go back and take notes or write down anything that you didn't get the first time. All right, have a good night.